Okay, so up until this point in time, we've had this concept where some device was running TCP/IP, the protocol stack. And part of TCP/IP meant that that device had to have a 32-bit number assigned to it, an IP address. And how that device looked at that 32-bit number was it a really old style device where it just looked at the first 8 bits and that was it? Or was it a newer device that used classful addressing where it said, well, I'm going to look at the first 2 or 3 bits there and determine if my address is A, B, or C. And then based on that, I'll figure out where the dividing line is between my network bits and everything left over, my host bits. Well, even though this classful addressing did end up giving us thousands and thousands of more available networks, even that very soon became apparent that it was not going to be enough. It wasn't going to be enough. So it soon became apparent that, hey, look, if a company goes to their regional internet registry or a service provider, and that company says, look, I'm really big, and I'm going to need 1,000 networks. I've got 800 different departments of employees. In addition to that, I want all my printers on one network. I want all my voice phones on another. I want all my fax machines on another one. So I actually need 1,000 broadcast domains, 1,000 networks. Well, if their regional internet registry or their service provider gave them 1,000 public classful networks, at that rate, those classful networks were soon going to be gone. So this is where in 1985, the concept of subnets came into play. So originally we had this, right? We have a building, 4 floors on the building, and let's just assume that each floor requires its own unique network. So back in the classful days, we said, okay, we'll give each one of those floors its own unique classful network. The 20, the 21, the 22, and the 23 networks. But that wasn't very scalable. Even that was going to run out. So instead they said, okay, here's what we're going to do. We will give you a single classful network, the 20 network, the Class A 20 network, and you will now divide that one network into multiple smaller pieces, what we call subnetworks. Now in a classful scheme, if all those devices in that building on the right were doing classful IP addressing, they would say, we're all in one network. We look at the first byte, and the number 20 in binary starts out with 0, right? The 128-bit is off. So they say, oh, the 128-bit is off, which means that this is a Class A address, which means the first byte tells us our network. Oh, the first byte's the number 20. Okay, anything beginning with the number 20 is in my network, belongs to my group. But clearly that's not the case here. Here we've got 4 different broadcast domains. So with subnetting, we're saying, hey, look, don't worry about your class. Your class is kind of irrelevant. Don't look at the first bit or 2 bits or 3 bits. Instead, look at something else. So now you're not going to look at your class identifier anymore. Now I'm going to give you a new piece of information that tells you of that 32-bit number where to draw that dividing line between the network portion and the host. And this is where a subnet mask comes into play. Can't do subnetting without a subnet mask. So we know, as a review, that when you get a network from an ISP, you're going to have the network part and the host part. Now from the ISP's perspective, the service provider, they don't care what you do with your host bits. They're going to assume that you're just going to assign those host bits and unique combinations to your laptops and your PCs and your servers and so on and so forth. But what they do care about is they say, look, we just gave you, let's say, an 8-bit network. We gave you the number 20. So the ISP says that is now registered to you. No other company in the entire world can have that 8-bit pattern on their network. That belongs to you. And we will make sure that we advertise to all the other ISPs throughout the entire world that the 20 network belongs right here. So in Germany, Mongolia, China, if you guys ever need to send a packet to something starting with 20, send it here and we'll get it to this company, which is, our customer. So it's very important that the network they gave you, the network bits, you don't mess around with those. Because if you start changing your network bits, now you're infringing on some other company. So let's say, for example, an ISP leases you this network, 129.1.0.0. Now, if we're dealing with a classful architecture, classful IP addressing, you would look at that and you say, okay, let's see, 129. Let's convert that into binary. 128-bit is on, so 120-bit is on, 64-bit is off, boom, I'm done. That is a Class B address, which tells me that the first half of that address, the first 2 bytes, 129.1, is the network. So this is what the ISP is thinking. The ISP is thinking, okay, Keith Company over here that we just leased this network to, they own 129.1. Nobody else in the whole world owns 129.1. So there's what it looks like in binary. So the ISP says, don't change those bits in red. If you do, we're going to be very unhappy with you. But you can do whatever you want with those last 16 bits. Those are host bits. So the ISP's assumption, the service provider's assumption, is that I have one network, one broadcast domain that uses that 16-bit pattern to identify itself, 129.1. But that raises the question, well, what if I have other broadcast domains? What if I need 2 networks or 3 or 4? Well, certainly the ISP would be more than happy to take my money to buy another network and another and another. The ISP would say, oh, sure, yeah, we'd love to sell you 129.2 and 129.3 and 129.30. Come to us with your money, we'll give you as many networks as you need. So I say, well, you know, if I'm spending $100 a month on that one network, I don't necessarily have another $2,000 a month to spend to get a couple dozen more networks. So remember, the ISP says, look, as long as you don't change those red bits, that's all we care about. So I say, well, wait a second. We know that all the devices in the same broadcast domain all have to agree on what the name of their group is in binary, what the binary pattern is for their broadcast domain, what their binary network is. I know I can't do anything, I can't change the first 16 bits. But why don't I do this? Why don't I give them a unique 18-bit pattern like this? I'll keep the first 16 bits the same because I can't change that. That's what my service provider gave me. But of the last 16 bits, I'm going to take those 2 bits there in green. Instead of telling my laptops, hey, look at those 2 bits as part of your host pattern, I'm going to say, no, I don't want you to do that. All laptops on that segment on the left there, of your 32-bit number, for all of you, the first 18 bits represent your network, represent your group. So basically what I've done is I've taken these 2 green bits here that used to be host bits, and I've repurposed them, I've converted them into networking bits. I've added them to the existing 16 networking bits I already had that I couldn't change. And because the ISP doesn't care what I do with these 16 bits on the end, I can do whatever I want with that. So I say, okay, all you guys here on the left, this is your 18-bit network. And all you guys on the right, I'll use a different 18-bit network for you. Still keeping the 16 bits I got from my ISP consistent, but now this is what's called subnetting. Subnetting is taking one network and dividing it into 2 or 3 or 4 or 5 or hundreds of sub-networks, keeping the original bit pattern of your original network consistent across all of them. So in this particular example here, of my 32-bit number now, we can classify those 32 bits into one of 3 buckets. We've got our original networking bits, which are the ones in red. Those are the ones I can't change, that I bought and paid for from my regional internet registry or from my service provider. And then we have some host bits, which are no longer host bits, which I've now repurposed or reused as networking bits. I'm not telling my laptops, add that to your existing network section. That's part of your group name. And those are called subnet bits. And I've got my host bits on the end. So here's the question. original IP. Devices just assumed back in the 1960s, the first 8 bits represented their group, represented their network. Move forward to, what was it, 1985, I think it was, or 1981, it was in the slides back, to classful addressing. Now a device took a look at the first few bits of the IP address and said, what class am I, A, B, or C? That'll tell me where my network ends and where my host portion begins. Now we're saying, as a third alternative, don't use either one of those methods. I'm going to arbitrarily tell you that of your 32-bit number, the first 18 bits, or the first 20 bits, or the first 28 bits represent your group. But how do I give it that information? How do I tell it of those 32 bits where that dividing line can arbitrarily fall? And that's where a subnet mask came into place. So here we see, prior to subnet masks, just the first few bits identified how much of the address belonged to your network. And then you were done. That was it. You fell into an A, B, or C, and that's all you had. So in this particular case, the PC on the left says, okay, I've now identified my network number as being 129.1. So if I need to create a packet, and if the destination of that packet is also 129.1, great. I know they're on the same wire as me. I know that when I put my electrical energy on this wire to represent ones and zeros, they will see it because they're in the same broadcast domain as I am. But if I need to create a packet going to a destination that's not 129.1, that's anything else, they are not in my broadcast domain, which means I need to send it to my router to get it to wherever it needs to go. So it says, okay, of my particular network, my network is 129.1.0.0. And if I ever need to send a broadcast, well, my group is 129.1, and I'll set all the host bits to 1s. So the broadcast address for this particular network is 129.1.255.255. Okay, now we go into subnet masks. So now on my laptop or my PC or my tablet, I have to provide it 2 pieces of information. The IP address, and right next to that, another 32-bit number in binary, which is called a subnet mask. And the 2 are used to compare against each other. Now here I put them one on top of each other to make it real clear. I said, okay, here's your 32-bit number, which is your IP address, and just below that is your subnet mask. And the way that your laptop or smartphone or tablet looks at this, it says, okay, I'm going to do a 1-for-1 comparison. For every bit in my subnet mask that's a 1, that means the corresponding bit in the IP address belongs to my network, belongs to my group, my broadcast domain. And for a bit in my subnet mask that's a 0, that means the corresponding bit in my IP address belongs to my own unique host identifier. So now here with this subnet mask, I'm telling it, okay, don't worry about the class anymore. Forget about the fact that it says 10 at the beginning. That's irrelevant. Instead, the subnet mask says, of your 32-bit number, the first 24 bits represent your specific group, your broadcast domain. So now the laptop says, okay, based on that, anybody else I want to talk to who's in my broadcast domain, who's on my wire, should also have the exact same 24-bit pattern as me, which is 129.1.1. And so now, if I need to send a packet to anybody that does not match those first 24 bits, that means they're in a different broadcast domain. And I'll need to use my default gateway. So now my network has changed a little bit. My network is still the same, 129.1.0. Remember, previously, he said, oh, my network is only the first half of the address. I'm class B, so it's 129.1. Now he's saying, oh, the subnet mask is telling me it's 129.1.0. I got to include that 0 as part of my network address. And if I want to send a broadcast, that'd be 129.1.1.255. So this is the purpose of the subnet mask. It's a comparison tool to help the device with the IP address to know specifically of those 32 bits, where the dividing line ends. Which portion of the 32 bits are the network and which portion are unique host bits. And we represent subnet mask in one of three different ways. Typically you won't see it in binary, but this is how your laptop sees it. It's just a string of binary bits. But typically we convert, just like we convert a 32-bit IP address into dotted decimal, we do the same thing for the subnet mask. We take that entire 32-bit binary number and convert it into dotted decimal. So this would be a common representation, 255.255.0.0. And a lot of times in papers and books and stuff, they'll shorten it even further. And they'll say, okay, well, in this combination here, I'm seeing that the first 16 bits are all ones. So that's telling me that of my 32-bit number, the first 16 bits are the network portion. So shorthand notation would be /16. Well, guess what? I have some more questions for you. So here we go. Let me expand this a little bit. A few more quiz questions. Same thing. I will give you guys 30 seconds to think about it, and then I will show you the answer. So here we go. Quiz number 3. Given the following subnet mask in binary, what is the equivalent representation in dotted decimal and shorthand? Okay, time's up. So here is our answer. So if you take a look at all the ones and remember that your ones represent your networking bits, if you just add them up, we've got 8 plus 8 plus 4, which says of the 32 bits, the first 20 of them are networking bits. So that gives us our shorthand answer of /20. And if you convert this into a dotted decimal number, all ones is 255, 255, and the first 4 ones, if you add those up, 128 plus 64 plus 32 plus 16 gives you 240. So that's why answer D is the correct answer also. Let's do a couple more of these. If the following subnet mask were to be applied to a PC's NIC, how many bits of the IP address would be interpreted as networking bits? All right, and the answer to this, 29 of those bits would be considered networking bits. Let's just do that one on the whiteboard real quick. So we had 255, so let's just make this a little bit larger. We had 255, 255, 255.248. So if we take a look at that, we know the number 255 is that. So that tells me that all 8 bits of the first octet are networking bits, all 8 bits of the second octet, and all 8 bits of the third octet. And then if we take a look at the number 248, that's the first 5 bits as being networking bits. So if you add all those up, 8 plus 8 plus 8 is 24. 24 plus 5 gives us what subnet mask would be appropriate in dotted decimal to indicate to a host that the first 26 bits of its IP address should be considered as the network. All right, the correct answer for this one was answer B. The first 26 bits of the IP address. So if we're looking at the first 26 bits, that looks like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's the first 24 bits. 1, 2, so there's 26. 3, 4, 5, 6, 7, 8. And when you convert those numbers, you've got 255.255.255.192. Given the following IP address and subnet mask, identify the subnetwork address of this host. So what you have here is a full 32-bit host IP address. When the host IP address, when that host looks at that IP address that he's got, as well as his corresponding subnet mask, what is the network that he will assume that he is on, that he's sitting on? Now remember, the key thing here about this is, in a 32-bit IP address, if all the host bits are zeros, that is your network number. So you're trying to extract from this what the network is where all the host bits are zeroed out. Okay. The answer to this one is answer A. So let's work through the logic of how this one works. So here we had 137.54.101.77. And the corresponding subnet mask was 255.255.224.0. Now, whenever you see within a subnet mask, if an entire byte is the number 255, remember that's real easy, right? That means that all 8 bits of that byte in the corresponding IP address belong to the network. So that means that this entire byte of 137 belongs to the network, and this entire byte of 54 belongs to the network. Now, where it may have gotten a little difficult for you was in the third byte, because we don't have all 8 bits. 224 is this number. That's 224, which tells me that of the number 101, only the first 3 bits belong to the network. And then everything else to the right needs to be zeroed out as host bits. So to do this, we had to convert the number 101, just the first 3 bits of it, into binary. So with 101, the 128-bit is off, 64-bit is on, 32-bit is on. 64 plus 32 is 96. At this point, we can't go any further because if we turned on the 16-bit, that would be too high. And then everything else needs to be zeroed out. 1, 2, 3, 4, 5, 6, 7, 8. So this is telling us here that these bits here in the pink boxes all belong to the network. Everything else are host bits. So when you convert that entire thing into a dotted decimal number, that's what gave you your final answer of 137.54.96.0. Because remember, to identify the network, that means all the host bits have to be zeroed out. What if I were to ask you, using the same IP address and same subnet mask, to identify the broadcast address of this network? Remember, what makes the network address different than the broadcast address? And the network address, all the host bits are 0, because you're referring to the wire itself, not any particular host on that wire. You're referring to the broadcast domain in general. Well, in a broadcast, you're saying, I'm sending it to all the hosts, every single host there is. So 011 ends my network, and if I'm sending it to all my hosts, it looks like that, because all my host bits are set to 1s. So to identify the broadcast address, it would be 137.54. And then what's this entire byte right here? Well, that entire byte, what is it? That's one number shy of the number 128, isn't it? Because the next binary pattern bigger than that would be 1000000, which is 128. So that means that number is 127.254. So using that one IP address and subnet mask, we were able to extract from that, and this is exactly the way your laptop does it. It extracts from that the network address. It says, okay, once my networking bits end, I'm just going to zero out everything. That's the network. That's the broadcast domain. That's my group. And it says, okay, and if I turn all those host bits to 1s, that's how I send a broadcast to everyone in my group. Let's do another one. Given the following IP address and subnet mask in binary, identify which of the answers below provide for the broadcast address of this network. We just did that. So let's see if you can do that for yourself. Okay, time's up. So if we take a look at this, according to the subnet mask, this right here belongs to our network because the subnet mask says the first 16 bits belong to the network. So what is that number? Well, that's just by process of elimination. You can pretty much assume it's 67 to begin with, and then the second number is 3, so that eliminates answer D. That can't be right. So 67.3, and we're being asked to identify the broadcast address. So that means that all of the host bits have to be set to 1s. So that means it would be 67.3.255.255. And that gives us our answer. Let's do a couple more. Want to make sure you really have this. Different permutations of the same question. Given the following IP address and subnet mask, identify which of the answers below provide for the broadcast address of this network. So very similar, but a little bit different. I'll give you 30 seconds for this one. All right, time's up. So in this particular case, the subnet mask was real easy. Right? It tells us that the first 3 octets belong to the network. And so if we take our host bits and we set them all to 1s to make a broadcast, that gives us our correct answer of 130.54.6.255. Okay. Let's do another one. Given the following IP address and subnet mask, so now we're back in binary, identify which of the answers below provides for the broadcast address of this network. 30 seconds beginning now. Okay, so in this one right here, we've got all of this belongs to the network because that's what matches our subnet mask pattern. And so if we're going to identify the broadcast address, that means all these remaining host bits have to be set to 1s. All right, so this right here, that's easy. If that's all set to 1s, that's 255. So we've got 67.3, and then in the third octet, if we have 0, 1, 1, and then we set the rest of it to all 1s, that would give us 67.3. I made a mistake here. It's not just the first 3 bits. Not just the first 3 bits. It's the first 4 bits. The network mask did not quite line up underneath. That's where we ended. First 4 bits there. So now if we set the remaining stuff to 1s, that third octet, if we convert that into dotted decimal, will give us the number 111. 0110 1111 is the number 111. One more quiz question. One more, and then we'll keep going on. Same type of thing. Identify the broadcast address for this network. Time's up. Correct answer was the bottom one. In this particular case, 255, 255, 224, that tells us that all of 77, all of 42, and then of the number 200, the first 3 bits, because 224 is 111, and then all 5 zeros. Kind of hard for me to draw it here, so forgive my sloppy drawing. That's 224. So of the number 200, we've got the first 3 bits we're concerned with. So the 128-bit is on, 64-bit is on, 32-bit is off. That gives us the number 192. Everything else is host bits. So if we're trying to identify the broadcast address, we have 5 more bits here. So let's go ahead and draw those in. 1, 2, 3, 4, 5. and then 1, 2, 3, 4, 5, 6, 7, 8. So 77.42, this is the number 223.255. That is the broadcast address of that network.